Hi, this is the review for our Exam 5, Chem 112. Today I'm going to talk about voltaic cell, and you'd have questions from voltaic cell. Let me give you a background and at the same time do a couple of problems from voltaic cell. Now, voltaic cell deals with spontaneous reaction. That means you just start that reaction and that's going to give electrical energy, and that's voltaic cell. If you force a reaction to happen, that's not voltaic cell. In that case, it would be called electrolytic cell. So voltaic cell, we'll be first discussing about voltaic cell. Their voltaic cell could be of two types. Any cell, in chemistry we use the word cell for something like battery, which would give you electrical energy when you connect those two ends together. So let me go over one problem from the book. This is chapter 20, problem number 70, and this is going to be our practice problem number 23. So this is practice number 23. Now, in this problem, we're dealing with a voltaic cell. Let me draw the picture of it and give you an idea. So you have two compartments here, and we have a salt breach. So this is salt breach, which maintains neutrality. Okay, and in this problem, they're telling you that there is only one type of electrode, which is silver chloride, solid, and this is the reaction that happens, giving silver solid plus Cl minus aqueous. So this is the reduction. Now, why this is the reduction? Reduction means absorption of electron. Oxidation is happens when something gives off electron. So this is absorbing electron, so this is reduction. In any voltaic cell, you must have one half cell giving off electron, another half cell has to receive electrons. So in this particular case, this is receiving electron, and obviously that's the reduction part. And in class I often mention this to remember that cat red, even though cats are not usually red, but this is how you can remember it. Cathode reduction. So in voltaic cell, cathodic reaction is a reduction reaction. And this is the reduction reaction, and that's the cathode. So let me write down here. So cathode reduction. Now you need to have an anode where oxidation takes place. Now it is the same electrode. So you just reverse the reaction. So anodic reaction would be just the reverse reaction of this. So let me write down here anodic reaction, and that would make this anode just the reverse reaction. I would have silver solid plus Cl minus aqueous. That gives silver chloride solid plus electron. What is happening is this reaction is going to absorb electron, and this reaction will give up electron. So this is going to act as an anode, which is give up electron, and this would be the receiver of electron as a cathode. In every electrochemical reaction, you'd find that one half of the reaction is going to give up electron, another half is absorbing electron. So I often compare it with a football game where quarterback is throwing the football and receiver is going to receive the football. But sometimes in actual football game there is fumble. But in this case there is no such fumble. whenever somebody is throwing electron, there has to be a receiver to receive electrons. Then and only then, electrochemical reaction is going to happen. So keep that in mind. If there is any particular substance going to give up electron, there has to be something to receive those electrons. Otherwise, there will be no exchange of electrons. So this part is going to act as anode, this part is going to act as a cathode. So cathode reduction, anode oxidation. So I ask students to remember this N-ox cat red. So that way you know that in the voltaic cell, always the reduction happens as cathode, oxidation happens in anode. Now next question that we need to deal with is, there are two concentrations given in this problem. One is 0.0, let me write down those concentrations. Cl minus concentration, 0.015 molar, and Cl minus for the other compartment is given a 2.55 molar. And in both cases we have the same electrode, silver. So this is silver, and you have silver sulfide at the bottom, that's the solid, and Cl minus is in the solution. So Cl minus here, and there is an electrode here. So this is silver, and you have a voltmeter here that would show you how much voltage you got. So that's basically the setup. Now, in this problem, they're asking you to identify which of these compartments would act as anode and which of the compartment would act as a cathode. Remember, oxidation, anode means oxidation, cathode where the reduction takes place. So let's now look into this, and basically we need to know Cl minus, would this be the higher concentration one? That would be an anodic compartment or cathodic compartment. That's what you need to figure out. Now this is what we call concentration cell. Two electrodes are identical, same electrodes, same electrode reaction. So there will be no contribution coming from electrodes, because in voltaic cell you get voltage from the fact that two electrodes, when they're different, they would have different oxidation or reduction potentials. So there'll be one contribution coming from electrodes and another contribution if there is any concentration differences of substances present in the solution. But in a concentration cell, both electrodes are same, so there'll be no difference in contribution coming from those electrodes. But so only difference in this case is the concentration of Cl minus. So as long as that concentration difference is maintained, you'd expect a voltage. And so that's why this is called concentration cell. So this is the type of voltaic cell that gives you voltage because of concentration difference. So as you draw electricity, it's not going to go on forever. What happens is, as you draw electricity, the lower concentration has to go up, and the higher concentration has to go down. Finally, these two concentrations will be same, and there'll be no flow of electricity. And that's when your battery is not going to work anymore. Now you may be thinking, why is like this? Why 0.015 cannot go down and Cl minus would not go up? If that happens, then you get electricity forever, and that's not possible according to second law of thermodynamics. You can't get energy forever. I mean, there's to be supply of energy. So whatever chemical energy we have will be running out of those. So basically, you know that there's a limit. So as you draw the electricity, lower concentration has to go up, higher concentration has to go down, and finally they should have the same concentration when there be no more electricity. Okay, with that in mind, lower concentration has to go up. Come to this reaction. As this reaction happens, what happens to Cl minus? This concentration would go up. So that means I must have a lower concentration for this cathodic reaction. So that means 0.015 molar would be here. So that means this part is going to act as a cathode. Now we are identifying it. Because it has the lower concentration of Cl minus, it would go up with time, and it would go up only when this reaction we choose for lower concentration. Because this, think it this way, as AgCl reacts, 1 mole of AgCl reacts, you get 1 mole of Ag, and you get 1 mole of Cl minus. That means it's going up. If 2 of them react, you get 2 in here. That would go up. So that's why lower concentration would be within the cathode. This would be the higher concentration, 2.55. Let's double check. As this reaction happens, silver is going to consume Cl minus. That means whatever concentration you have, that concentration will be lowered because silver is reacting with it. So in other words, reaction of anode can explain depletion of Cl minus concentration in that compartment. And that's exactly what we want. We want this to go down, this to go up. That way we are not going against second law of thermodynamics. Basically you start with a difference, but gradually that difference goes down, and this is how it can be achieved. Okay, so now we identified anode and cathode. This is cathode, this is anode. Make sure you understand that. Let me repeat this. How we got anode and cathode is the same reaction. In anodic compartment, you'd have oxidation reaction where my product would have electron. Cathodic compartment, electron would be absorbed or received, and then you get the final products. Then we need to know that which of these two concentrations would be making the anode and which one would be making the cathode. The lower concentration has to be in here because that has to go up with time. And only this reaction explains that as this reaction happens, product concentration would go up. Second reaction, as that happens, Cl minus concentration has to go down because silver is going to consume Cl minus. So both these are right now, and my assignment is right. So this is going to be cathodic reaction, this is going to be anodic reaction. So this half is going to act as anode, this half is going to act as a cathode. So we can now calculate some numbers. Let's first add up. Electron cancel out. And I have 1 mole of electron being transferred. So this is very important in electrochemistry, how many moles of electron being transferred from one half cell to the other half cell. And there has to be a balance. That means you cannot have 2 here and 1 here. You'll have to balance it so that it's the same number of electrons. And that's we call n value equals to 1, and we plug in an expression to get EMF or voltage of the cell. So let's now add up. Silver would cancel out. It's the same silver solid. Silver chloride would cancel out. So now I have 2 things remaining. Cl minus, aqueous, 2.55 molar. On the reactant side, on the product side, I have Cl minus. Make sure you understand this part, because it's very important that we all understand this. So now, even though you have the same reactant and the same products, species-wise, but the concentrations are not the same. 2.55 for this Cl and 0.015 is for this Cl minus. So it's not really, in real sense, identical. So we are going to make use of these numbers in a minute. Let's first do part B. Part A, they were asking which one would act as an anode, which one would act as a cathode. So we already gave you that answer. This is anode, where you have high concentration, cathode where you have the low concentration. Because this explains increasing of concentration of Cl minus, this is decreasing concentration of Cl minus. Next is the calculation of E0 cell. E0 cell would be given by E0 oxidation plus E0 reduction. Contribution coming from here plus contribution coming from here. It's saying equal and opposite. So I don't need to know the value of this half cell potential. Even if it is given, say this is plus, one is say plus, I'm just making its number, plus 0.50, the other one has to be minus 0.50. So this would be equal and opposite, so it's going to get 0. So for same electrode in concentration cell, one would be plus, the other would be minus of the same value because it's the same electrode. So there is no contribution coming from standard cell voltage. Standard means at room temperature, the voltage when concentration is 1 molar. That means each of these has 1 molar concentration. Part C, what is the EMF of the cell? Actual cell is not under standard state. Just by looking at these concentrations, you know that it's not standard state. In order to be in a standard state, each one has to be 1 molar concentration. So this is 2.55, not 1 molar. This is 0.015. So it's not under standard state. So we have to use this expression. E cell will be given by E0 cell minus, I'm going to use the expression that is given in the book for room temperature. And you know that we can write down as RT over NF log of Q. For most problems where you deal with 25 degree or 298 Kelvin and F is Faraday, 96,500 Coulomb, and R is 8.314. So when you do all this math, and you finally end up with more simplified expressions. So I suggest that if the temperature is at 298, just use this expression that I'm going to write down now. E0 cell is standard EMF, which is 0 in this case, and you'd find 0.0592 over N, and log of Q. What is Q? Look at this reaction, products over reactants. My product concentration is 0.015. Reactant concentration is 2.55. And we already know this value of E0 cell equals to 0 because it's the same electrode. One is going to be equal to the other. And N value we already know there is transfer of 1 mole. So N equals to 1. So this is equals to 1. Because 1 mole of electron is being transferred from one half cell to the other half cell. And that's N value. So if you do the math, this is log with base 10. So we get 0.132 volt. So that's the answer to this question. So in this voltaic cell, concentration voltaic cell, cell voltage is 0.132. Standard voltage is 0 because it's the same electrodes. Under standard situation, there will be no voltage. Now we're going to do the next problem. Again, it's on voltaic cell, which will be our practice problem number 24. Okay, now this is practice problem number 24. Again, I'm picking one problem from the book for your practice. Chapter 20, number 65. This is Brown and LeMay book. It is 12th edition of the book. Let me write down the reaction given. Zinc solid plus Ni2 plus aqueous giving zinc 2 plus aqueous plus nickel solid. So this is an electrochemical reaction. This is the overall reaction. In order to calculate EMF or voltage of a cell that gives you this reaction, you need to split that into two half reactions and figure out how many electrons are being transferred from one half cell to the other half cell. So we're going to show that in a minute. And then in this problem, they also want you to get EMF of the cell or voltage of the cell. And they gave two concentrations for part B. So part A is for E0 of the cell. So let me write down part A. What is the E0 cell? Half cell potentials are given, and we're going to write down that half cell potentials. So let me first split that. And B, what is EMF? EMF is the same as voltage. When the concentrations of zinc 2 plus is given, and also nickel 2 plus is also given. So let me copy those two numbers. 0.100 molar, and nickel is 3.00 molar. Okay? So in order to do this problem, first we need to split this reaction into two half reactions. From similarity, I can split this quite easily. Zinc going to zinc 2 plus. This is aqueous, this is solid. Now you're not balancing it. The rule is first you balance the element. I have one zinc plus, and so the zinc is balanced. If then you have oxygen, then you balance it by adding H2O. Then you balance hydrogen by adding H plus, and finally you balance electron or charges. Now here, I don't have any oxygen or hydrogen, so I don't need to worry about that part. Only thing is I have the charge difference, +2 here, so I need to balance, because this is no charge here, it means 0. I must add 2 electrons. Only thing you can add would be electron. So 2 electrons would make it -2. +2 minus 2, that makes it 0, so it's balanced. That makes one half reaction. Let's look at the other half reaction. Nickel 2 plus aqueous. Aqueous means water solution, giving you nickel solid. Again, it's the same number of same element, so number is balanced. So now I need to balance the charge. This is +2, this is 0. So in order to make it nickel, I'll have to have 2 electrons on this side. So that means -2 + 2, that makes 0. So now I got these two half reactions. This is oxidation because electron is given off. So this is oxidation, and remember, N-ox. Anode oxidation. So this is anode. Red, cathode reduction. So this is reduction because it's absorbing electron. So that's cathode. Okay, now total number of electrons has to be balanced. This is the number of electrons being transferred from one half cell to the other half cell. And if I add them together, I'm going to get the same reaction that you see here. So now here we found out N equals to 2. The sum of these two is already in here, so that's we got it. So what we're going to do next is going to do this calculation for E0 cell. These two values are given with this problem. Let's first write down here. This is E0 This is easier for the second. Standard half cell potential for anodic reaction. And here is oxidation taking place. Zinc is oxidized. Here, reduction taking place. So it's nickel 2 plus is reduced. So that's why I'm using this subscript, ox and red. Book would always write down these values in reduction value. So you'd not find oxidation value, you get the reduction value for zinc. And basically, this is for this same reaction, opposite reaction, it would list like this. Let me show you. Zinc 2 plus 2 electron giving zinc, and E0 reduction, because this is the reduction, that's listed in the book as minus 0.763. But that should be enough for you, because you just reverse, you're using the reverse value, reaction for the reverse reaction. So when you reverse the reaction, reduction becomes oxidation. So that's what we need. And the value would remain the same, but the sign gets changed. So it's a 0.763. So from reduction value to oxidation value, change the sign. Positive becomes negative, negative becomes positive. So book value is minus 0.763 because they gave reduction value. And since we need oxidation value, so we're using this number. This is the reduction reaction, so I can use just the book value because they list all these reduction values, and the value is minus 0.28. So what is the standard cell voltage? That means if I run this experiment with this zinc and nickel and assume that concentrations are all 1 molar, then I'll be getting E0 cell or cell voltage under standard state. And that value will be given by E0 oxidation plus E0 reduction. It's like any football game where you have a contribution coming from both quarterback as well as receiver. In this also, contribution is coming from who is oxidized and the one which is reduced. Both are happening at the same time. So both would have contribution towards cell voltage. So it'd be 0.763 minus 0.28. I just added these two numbers, and that would give me 0.483. So if this reaction happens under the standard state, 1 molar concentration of zinc, 1 molar concentration of nickel, the voltage that you're going to get will be 0.483. That's answer to part A. So now we're going to do part B, where they're saying that to calculate EMF of the cell when the concentrations are not 1, rather zinc is 0.1 and nickel is 3. So under non-standard state, you're going to use this. EMF of the cell equals to a standard state value minus 0.592. I'm going to use that expression. Divide by n, log of Q. N tells us how many moles of electrons being transferred, and we already know it's 2. 2 moles of electrons being transferred from one half cell to the other half cell. Always you get that after balancing. So I can write down now E cell equals to, I already got E0 cell, 0.483 volt minus 0.592 over 2 moles of electrons being transferred. Log of Q is the same, you define it same way as equilibrium constant. So product values on the top, which is zinc 2 plus value will be on the top. So zinc 2 plus value on the top, and that will be raised to the power 1 because there's only one zinc. And nickel 2 plus on the bottom. You ignore the other ones because those are solid. This is a heterogeneous equilibrium where you ignore solids mixed with aqueous solution. So now we can plug in our numbers, 0.483 minus 0.592 over 2 log of, now we have these values given, zinc 2 plus value is 0.100, 0.100, nickel value is 3.00, and I did this calculation, this is what I got, 0.527 volts. So that's the cell voltage of this particular voltaic cell when the concentrations are 0.1 for zinc and 3 for nickel 2 plus. So make sure you understand this types of problems on voltaic cell. One is concentration cell. This is where the difference was only in concentration. And this is other type of voltaic cell where you have different electrodes. So there is a contribution coming from the electrode. This is this part. And also from concentration. Now that concentration term would not be there if it's a standard state. That means you'd be then calculating E0 cell. Under standard state, these would be all 1. Log of 1 is 0. That means this term is going to disappear. There'll be no term like this when concentration is 1. Okay, now our last problem that I'd like to go over will be on electrolysis. Now in voltaic cell, you get spontaneously electricity, and reaction happens spontaneously when you join those two ends. This is practice problem 25. So other than voltaic cell, now we're talking about electrolytic cell. Electrolytic cell. So this is also from chapter 20. Again, I picked one problem from the homework, number 92, from Brown-Lemay book. The question is about electrolysis of molten magnesium chloride. Molten means melted. That means it's liquid now. And question is, how much, what will be the mass of magnesium that you're going to deposit? Normally that happens at the cathode compartment. How much magnesium will be deposited on the cathode if the current, the electricity that you'd be passing through is 4.55 ampere, and the time is 4.50 days. So that means you pass the electricity that many ampere. Ampere means coulomb per second. Coulomb is the unit of charge. 4.55 coulomb per second. How much mass of magnesium will be deposited on the cathode? Now already you see there's a discrepancy in the unit. This has second, this has days. So let's change first days to second before I proceed with this. So 1 day, 24 hours. So day would cancel out. And then 1 hour, we're writing down 3600 second. Hour would cancel out. So the time that I got is 3.89 times 10 to the power 5 second. So basically, you have that much current to pass for that many seconds, and then you need to calculate how much magnesium will be deposited. Let me draw this to give you a background of how this can happen. Quite often, different metals have deposit of gold, because that gives a longer lifetime of that substance. And how do we do that? Same thing, electrolysis. Electrolysis forces a reaction to happen. So you need to apply voltage from outside by using a battery. Okay, now in this case I'm going to show you how this happens. So this is one electrode, and this is the other electrode. So this is one, this is the other one electrode. My drawing is not that great, but at least I will try to explain to you. Now, molten magnesium chloride would have magnesium 2 plus and Cl minus. So you would have magnesium 2 plus, Cl minus floating around. And there are lots of these coming from the melted magnesium chloride. Now, I want to deposit, say this, I want to make it cathode because I want magnesium to be deposited here because I want this reaction to deposit. So in order to deposit magnesium, you want this reaction because that way magnesium becomes solid magnesium and it will be sticking to the electrode. So if I want to plate this particular electrode with magnesium, same thing I can do with gold. In that case, I'll have to have gold solution, Au, 2 plus or 3 plus, then undergo this kind of reaction, then gold will be deposited here. So the key thing is I'll have to make it a cathode. You have the whole control, depending upon how you're joining the battery. So here is your battery or voltaic cell. That's going to run this process, electrolytic cell. You know that every battery has a positive end and a negative end. Negative end is the one through which electron is pushed out. So I want electron to come over here so that magnesium gets attracted. So I want electron to be pushed out of this end. That means I want my negative end of my battery here. My positive end be here. So by thinking about the orientation of your battery, you can select which one is going to act as a cathode or where your magnesium or metal is going to be deposited. So since I'm making it a cathode, I must pump electron from this side. So this will be rich with electron, and that's going to cause this reaction to happen. So this is going to act as a cathode. If you switch the battery, this end goes over there, and this end comes over here, then this side of the electrode is not going to get the deposit of magnesium, rather that side will get. So this is going to be cathodic reaction. For this problem, you don't need to worry about anodic reaction, but for the completion of this discussion, let me also write down anodic reaction, where you have 2 Cl minus in the liquid that changes to Cl2 gas, and you have 2 electrons. So here you have 2 moles of electrons are being transferred. So this question is about deposit of magnesium. So we are only interested in this, and our problem to start from here. So let me show you this. 4.55 coulomb per second, that's the current that you are passing. Always start with what is given and then go forward. And I'm passing that for that many seconds. This is second, keep in mind. 3.89 times 10 to the power 5 second. So second would cancel out, that would give me coulomb. Now we know one constant, you need to know that 1 Faraday is 96,500 coulomb. That's same as 1 mole of electron. So 1 mole of electron would carry this much of charge, which is called 1 Faraday. So we can write down here now, 96,500 coulomb makes a mole of electron. So why I want to get mole of electron? So that I can make use of this reaction to get magnesium. So coulomb would cancel out, that gives me moles of electron. Now go back to this reaction, 2 moles of electron deposits 1 mole of magnesium. And since they want the mass of the magnesium, so we need to go one more step. 1 mole magnesium. And then from periodic table you find out the mass, which is 24.3 gram. So you get mole-gram relation from periodic table, which is 24.3. If you do all the math in here, and final answer is 223 gram of magnesium. So that's the answer. That means if you allow 4.55 ampere of electricity to pass through for 4.550 days, then you get a deposit of 223 gram of magnesium on the cathode. And that's the end of our discussion, and hope you'll be able to work on these problems.